Why do we need counter-propagation networks in artificial neural network architecture? To answer this question, we first need to understand the landscape of artificial intelligence and machine learning. These two fields have seen significant advancements with the introduction of various complex network architectures that aim to replicate and even transcend the capabilities of the human brain. Amidst these, counter-propagation networks, CPN, have carved a niche for themselves. Emerging from this backdrop is the CPN, often abbreviated as such. These are a type of feed-forward neural network. This essentially means that they function on a principle of forward motion, with no loops in their structure that would allow the data to be passed back through the network. This, in turn, fosters a highly efficient flow of processing and computation, a feature that is critical for the swift processing needs in the landscape of machine learning and AI. CPNs are distinguished by their unique blend of two popular neural networks. The first of these is the Cohonan self-organizing map, a type of artificial neural network that uses unsupervised learning to produce low-dimensional representations of the input space of the training samples. The second part of this blend is the Grossberg outstar, a mathematical model that offers an explanation of how certain neural networks can learn to recognize certain patterns in their input data. This combination in CPN creates a powerful network that can adapt and learn from a wide variety of input data, transforming complex mathematical computations into understandable and actionable results. It is this blending of unique features that makes CPNs an integral part of modern artificial intelligence and machine learning architecture. Now, to circle back to our initial question, why do we need counter-propagation networks in artificial neural network architecture? It's because CPNs bring together the best of the Cohonan self-organizing map and the Grossberg outstar, offering a robust, adaptive network that is able to handle complex computations with ease. A counter-propagation network has two layers, an input layer and an output layer. This network is a type of artificial neural network that is used to create an adaptive system capable of learning from its environment and making intelligent decisions. It is designed with complex algorithms to enable it to compute intricate patterns and relationships within the data that it processes. The first layer is the input layer, is also known as the competitive layer. This term derives from the competitive learning algorithm that it applies. The competitive layer essentially adheres to the Cohonan rule. The Cohonan rule is a learning algorithm of unsupervised neural networks, named after its inventor, Toivo Cohonan. This rule is instrumental in creating self-organizing maps that classify the input data into different categories. The job of the input layer is to classify the incoming data. It does this by mapping the input data onto the output layer, creating a system of organized information. This input data could be anything from complex mathematical equations to simple binary numbers. This process of identification and grouping is a crucial aspect of the counter-propagation network. The second layer is the output layer. This layer is guided by what is known as the rule. The Grossberg rule is another learning algorithm named after its creator, Stephen Grossberg. This rule defines how the weights of the network are to be adjusted based on the input data. Just like the input layer, the output layer has a specific purpose. Its job is to adjust the weights of the connections in the network. This adjustment is done according to the input data that is received, allowing the network to learn and adapt over time. The modifications made by the output layer enable the counter-propagation network to fine-tune itself and continually improve its performance over time. The output layer, on the other hand, follows the Grossberg rule and is responsible for adjusting the weights of the network based on the input data. What sets CPN apart is its unique learning process. This process is not just unique, but it's also pioneering in the field of neural networks. It's a two-step procedure that has been designed in such a way to optimize the learning speed and ensure swift adaptability. The procedure is simple yet intriguing, and it encapsulates the essence of how learning should be systematic, progressive, and adaptive. The first step is called the forward pass. In this phase, input vectors are applied to the network. Input vectors can come in various forms and complexities, but their role remains unchanged. They are the initial pieces of data that the network must process and learn from. The importance of the forward pass cannot be overstated. The first step where the actual learning begins, setting the tone and pace for everything that follows. Once the input vectors are applied, the network makes use of something called the competitive layer. This layer is designed to identify the neuron that is closest, in terms of attributes and characteristics, to the input vector. This neuron then gains the title of the winning neuron. This term is not just a metaphorical title, it signifies that out of all the neurons, this one has the most optimal response to the given input vector. This identification process is pivotal in ensuring the network functions optimally and learns effectively. The second phase is the backward pass. Here, the weights of the network, which are crucial determinants in how the network responds to specific inputs, are adjusted. And the basis for this adjustment? The earlier identified winning neuron. This adjustment process allows the network to learn from past experiences and optimize its future responses. In this way, the backward pass not only complements the forward pass, but also ensures that learning is an ongoing dynamic process. These two steps, the forward pass and the backward pass, working in unison, ensure the network learns and adapts swiftly and effectively. It is this systematic, unique process that the counterpropagation network utilizes that highlights its distinctiveness in the vast realm of neural networks. These two steps ensure that the network learns and adapts quickly. The beauty of counterpropagation networks rests in their dual capacity to execute both unsupervised and supervised learning methodologies, which, when combined, result in a powerful, adaptable, and versatile system. This dynamic combination allows for greater complexity in learning processes and an increased capacity for pattern recognition and prediction. At the heart of these networks lies the cohonan layer, a component responsible for performing unsupervised learning tasks. It operates by methodically mapping similar input vectors to nearby regions in the network's internal map. This feature empowers the system to learn autonomously, enabling it to understand patterns within the input data without requiring explicit guidance or external input. This process is akin to creating a topographic map of the data, with similar data points grouped closely together. Thus, it allows the network to form a comprehensive understanding of the data's underlying structure, thereby aiding in the identification and prediction of patterns. Balancing this functionality is the Grossberg layer, a separate but equally vital component of the counterpropagation networks. This layer performs supervised learning, fine-tuning the weights of the network based on the desired output. This aspect of the learning process is more guided and specific, serving to optimize the network's predictions and analyses by continuously refining its internal parameters. This fine-tuning process is essential for the network's learning capabilities, allowing it to enhance its predictive accuracy and improve the quality of its output over time. Through these combined learning methods, the networks gain the ability to effectively interpret, analyze, and respond to complex data inputs. The Grossberg layer, on the other hand, performs supervised learning, fine-tuning the weights based on the desired output. One of the key advantages of counterpropagation networks is their fast learning speed. The combination of the cohonan and Grossberg layers allows the network to quickly adapt to new data. This makes CPN ideal for applications that require quick decision-making, such as stock market prediction, speech recognition, and image processing. Another advantage of CPN is its ability to handle nonlinear data. Traditional neural networks struggle with nonlinear data, but thanks to the cohonan layer, CPN can easily map nonlinear data onto a linear output layer, making it a versatile tool for a wide range of applications. To sum it all up, counterpropagation networks are an integral part of artificial neural network architecture. They offer a unique blend of unsupervised and supervised learning, fast learning speed, and the ability to handle nonlinear data. The next time you come across a complex problem that requires quick decision-making or involves nonlinear data, Remember, counter-propagation networks might be the solution you're looking for.